So I'm now going to talk about a method for sampling from an arbitrary distribution using something called rejection sampling, which basically means we make samples but we throw some of them away, we reject them. So, as we know, it's easy to sample from a uniform distribution because we can use RAND, and we can easily sample from a Gaussian distribution because we can use RAND-N, which are both MATLAB functions. It's not quite so easy if we want something from an arbitrary distribution, because we can't just call a Gaussian or we can't just call a MATLAB function for these things. So what can we do? Well, one way is we could actually, if this is certainly in the one-dimensional case, we could actually calculate the inverse cumulative distribution function and use that to transform uniform samples to the one we wanted. And we sort of looked at that slightly last time. However, a sort of a more general method is using something called rejection sampling, and that's what we'll talk about now. There's other methods as well for doing sampling from things. One of them is Metropolis Hastings. MCMC means Monte Carlo, Markov chain Monte Carlo. And there's other methods like Gibbs sampling. We're not going to actually touch on other sampling methods, but it's important to know that there's a great pile of them out there that are used quite a lot. But we're just looking at some quite simple things here. These Markov chain Monte Carlo methods, or Monte Carlo Markov chain methods, don't result in independent samples, whereas what we're going to do will. Let's think about sampling from an arbitrary distribution. We're going to call it P of X. And like I said, there won't generally be a ready-made function that does this. So imagine we've got a function that looks like that, and we want to basically sample from this thing, and it's not a Gaussian, it's not uniform. How can we go about that? Well, we can't sample directly from P of X because it's arbitrary and it's not a Gaussian and it's not a uniform distribution. So what we can do is we can say, let's first of all choose a distribution that we can sample from. And this thing has got to span the range, right? It's got to span the range of the thing that we actually want to sample from. So we make sure that we choose something that's broad enough. And in this case, we could maybe choose a Gaussian, and that will span the range, as in fact, it spans a bit further than the range. In this case, you could also use a uniform, in which case it would just go straight up here, down, along here, and then down here. We're going to use a Gaussian as an example. I'm going to call this Q of X. This is the thing that we can sample from. Now, Q of X at the moment is actually not always above the distribution that we want to sample from. So what we've got to do is we've got to somehow scale this so that we have a curve which is always going to be above there. And the reason for that is we want to make sure that when we're doing the calculation, we can always have a value that we're going to be comparing with the value of the probability distribution, P of X, which is at least as big as it. We want to make sure that we have a value which is at least as big as the value that we're actually going to sample from the P of X. Otherwise, it basically won't work, right? So the idea is as follows. We're now going to draw a sample from the candidate distribution that we can actually sample from. So from our Q of X, we can draw samples from this, right? This is a Gaussian, that's why we chose it. Like I said, it could have been a uniform. We can actually sample from that. So what we do is we sample from this and we get some value along X, right? We'll get some value. Most of the time they'll be around the mean, right? Very, very, very rarely they'll be at the edges, but mainly we'll end up sampling and getting a sample which is sort of fairly round the centre. Now, if we kept all the samples when we do that, and then we calculated what does the distribution look like after we took a very, very large number of them, obviously what we'd end up with is a probability distribution that looks like Q of X, because it's basically that's what we're sampling from. But we don't want that to be the case, do we? We don't want it to be this candidate distribution. We want it to be the distribution of the target thing that we've got here. So we want the P of X to be the distribution of the samples. Now what that means is some of the time we're going to have too many samples, right? So at a certain value. Imagine we sample from Q of X and we get a value that corresponds to something like here, right? This point here. So you can see that the Q of X, the Gaussian, has got quite a high density at that point. However, the P of X hasn't. So if we kept all the data with that value that we sample, that gives a value around here, what would happen is, obviously, we'd end up with a density that's quite high at that point. But actually, in this particular case, at this line here, we want a fairly low density. So what we have to do is we have to throw some of the samples away, and we throw them away such that the resulting density will end up being quite low at that point here. And that's the idea. So the idea is we reject some of the samples, so we end up getting an overall distribution when we go to an infinite number of samples, which actually looks as if it's coming from the target distribution P of X that we want it to come from. Okay, so we've got to throw things away. So how can we do that? Here's the idea. What we're going to do now is we're going to scale this distribution then, so it's always bigger than the target distribution we want it to look like. So we're just scaling the function value. Don't forget, we don't have to actually scale probability densities as such, because it's something obviously that you can't just arbitrarily do. But what we do is we want to make sure that this function that we're going to consider, which is our now scaled Gaussian, is always bigger than the P of X. And then what we're going to say is the following, right? Let's now take a sample. We're going to end up with a sample from our Q of X, our Gaussian, and this particular value that we've chosen now just so happens to be X of S, which is this point here. And as we can see, if we draw a line all the way up to the top, we see that the density, if you like, of the Gaussian at that point is actually quite high, whereas the density of the target distribution is a bit lower. So this kind of gives us a nice way of saying how we can work out, with what probability should we throw away this sample. So if basically the distance from here, from the baseline to where this sample touches the top of the probability distribution of the target is given by VP, right? So the probability of X of S is that point there. We see then this distance from here to here along this line corresponds to a certain probability. Whereas if we go from here to all the way to the top here, where it touches the actual scaled candidate distribution, we see that line's a little bit longer. So the trick is to say, well, we want to keep samples in the proportion of the length of the line to the actual target distribution that we want, divided by the distance all the way to the top of the scaled Gaussian in this case. So it's going to be the ratio of this bit here, this length here, to the V of P point, divided by this V of Q point. That's going to give us a way of actually deciding, how many of the samples we want. So if we throw things away in that proportion, well, keep things in that proportion, then what we do in the long term is we end up with the density of the samples that we end up with looking as if they're coming from P of X as opposed to Q of X, right? So we've got this scaled density of what we've actually sampled from, but the actual target distribution has a lower value, a lower density at that point, and what we have to do is then throw away or reject samples corresponding to this little distance here and keep them corresponding to this longer distance here. So in other words, we only accept a sample, X of S, with a certain probability, and that probability is the distance here, this Px of S distance, divided by this Cqx of S distance here, right? So this gives us a probability that we actually keep the sample. And if we do that, we end up looking as if we're sampling from P of X as opposed to from Q of X. So let's actually now turn this thing on its side and think, how can we actually make that decision? Because what we're going to do is we've got to make a decision. We've got to make, with a probability given by this term here, that we keep the value, and with the rest of the time we throw things away. So this comes back to our how do we make a decision with a certain probability question that we went through earlier. I've just turned this thing on its side now, so we can actually compare what this thing looks like in comparison to how we were dealing with it when we were actually doing sampling from a uniform distribution. Because if we can sample from a uniform distribution, we know that we can already make a decision with a certain probability. So what we can see is this region here to here, this length here, that's the probability that we're going to keep it, and the total thing is the total probability of a particular sample from a uniform distribution. So what we're going to say is this distance here, which corresponds to the probability of xs divided by c qx of s, that's this distance here. The red bit here is the probability you want to keep it, and the whole distance here is the overall 100% probability of that we can keep it, but we don't want to do that. So what we're going to say is we're going to keep the data by making a decision with a probability given by p x of s divided by c q x of s. Otherwise, we're going to reject it. And we know that we've already done that, right? We've done that with our decision making before. All we have to do is say, we're going to keep. If this is now a uniform distribution between two limits, then it's only this red region where we actually want to build the keep the data point decision. And this is quite easy to then work out what this all means. What it's saying is we keep a data point with probability p x of s divided by c q x of s. So that's the retention probability. So we keep it if we have a probability given by that. And as we did before, we can use the rand function to make this decision, whether or not we keep it or not. If we just do it with rand, we know rand samples between 0 and 1. So therefore, what we can say is if the rand value that we get is less than equal to this p x of s divided by c q x of s, we keep the sample. Otherwise, we throw it out, right? So it's just a simple binary decision to keep or to throw away. So very, very briefly then, to quickly recap what I've just said, the way rejection sampling works. If we want to sample from something like p of x, which is arbitrary, first thing we need to do is find a candidate density which will span it, so it's wide enough to account for all the points that are actually going to ever be sampled from it, and then we scale it so it's always above it, right? So we scale it so the probability of x is always less than the scaled value of our candidate density, where c is just a factor, and then we have a simple algorithm to actually let us go through. First of all, we sample from the distribution q of x that we can sample from, and this gives us a value along the x-axis, right? And then for that particular value along the x-axis, we're going to decide whether or not we want that point or we want to throw it away. And in order to do that, we can use our rand function, so that will give us a value, it gives us a probability, and what we can say then is if that value then is less than equal to the probability that we want to keep this thing, so the probability that we want to keep it is px divided by c q of x. If the probability is less than that, less than equal to that, then we keep the value and keep the sample. Otherwise, we just throw it away. And we keep going around this over and over and over and over again until basically we're finished. I'm not saying it here particularly, but why is this sometimes not a good thing? Well, the thing about rejection sampling is we're actually throwing samples away, right? So we're wasting things, if you like. So that's one of the big problems, and it's a big problem if your candidate density is really greatly different than the actual target density. So imagine you had a very narrow, sharp p of x like a little impulse in the middle, then you're going to be throwing stuff away all the time. So it can be very inefficient. So let's just think of a very simple example written in MATLAB to illustrate how this is working. What I've done is I've got I've got a double sine wavy kind of function in green here, which represents what the distribution is I want. What I can do is I can say, well, I want to find a distribution which will span that I can sample from. So I'm going to choose this blue thing is going to be a Gaussian, but I need to scale it now. So I've got to scale it up to get the functional value that's always bigger than my actual target. So I've scaled it up so it's always above the green curve. So the red one's always above the green. And in MATLAB, all I'm doing to do this is I'm just setting up some Gaussian parameters here. I'm just building my candidate distribution, and I'm scaling it. So this is where I'm doing some sampling. I'm building my target, and I'm building my candidate function, which is just a Gaussian here, and then I'm scaling it with a certain factor, so it's always above. And basically the algorithm to actually do the sampling then is quite simple. All we do is we sample from the Gaussian that we can actually sample from. We get also the value of what's the density at that point of the Gaussian. We then get our scaled version of that. We then get the value of the target distribution at that point, and don't forget it's going to be this ratio that we care about. It's going to be the ratio of what the target is to what the actual scaled candidate is at that point, and then we make the decision. We want to know when to reject and when to keep. So basically we want to scale now. We want to keep a point if the probability is less than in this case, the target value divided by the scaled candidate value. So, and if we pick from rand, so all we have to say is if the value we get from rand is less, in fact less than equal to this probability of acceptance, then we keep the point, otherwise we throw it out. And that's basically all there is to it. And you can run that kind of thing, and this is an example. It was basically showing you that it's it's sampling from this Gaussian. Obviously this is the scaled Gaussian I'm actually showing the points from here, and all it's saying here is it's plotting them in red if it's throwing them away, and it's plotting them in green if it's keeping the samples. And finally you'll see if you actually run the analysis after collecting loads and loads of samples, you can end up getting to a reasonably good approximation in this case of what you had, what you were aiming for.